Okay, next we're looking at Charles's law, and this is about volume of gas and temperature of the gas. And it's that the volume of a gas at a fixed pressure is proportional to the temperature. Now, we already know that the kinetic molecular theory of matter tells us that molecules are continually moving. So as we increase the temperature, they get more kinetic energy, they move around faster, and they also move further apart. This happens in solids, liquids, and gases, but it's very noticeable in gases. And that's what we're looking at here. So it will then cause an increase in the volume of the substance or expansion as we heat things. So if we're keeping this as a constant pressure on the gas as we heat it, we should actually see an increase in volume as the temperature increases. And this diagram here shows that. Here we have one temperature and the volume of the gas here. And then if we heat it more and we get a higher temperature of gas, the volume increases. Notice that the moles of one is equal to the moles of the other. The number of particles, two, is going to be the same. And that's really important here. The pressure of one is also going to be equal to the pressure of two. Okay, so they're not changing. That's really important for this law, for all of the laws. So when V is proportional to T, we can write that as volume is a constant times the temperature. So in this case, again, a constant is an unchanging number in this relationship. So V might change, and the amount that T will change is based on that constant, as long as you're not changing pressure and amount of molecules. If you do change that, that's what K changes as well. So it's for a set temperature and volume and amount of gas. So we can actually see this in our graph below here. All right, so here this graph is showing you along the bottom, just rub that extra bit out, we've got the temperature. So this is going from low temperature to high temperature. And the line here in the middle is the line of the freezing point of water, 0 degrees Celsius. Okay, we have no numbers apart from that one, and the next one I'll show you in just a moment. So as we increase the temperature, the volume is going up by the same amount. Okay, so this change here in temperature and volume is going to be the same as the change in temperature and volume here. Okay, this actually, if I just go back a bit, this is where we get, again, V divided by T, divide this side by T times the V side by T is equal to K. So V1, T1. And since K has to be the same for the same substance there, V2 over T2 is also going to equal that constant. So we can use this as a way of figuring out a gas that we don't know. Now, with this linear one, this is the interesting fact that they figured out, is that if you keep extrapolating this line all the way down to where you have a volume of 0, okay, you end up at a temperature at minus 273 degrees Celsius. So this temperature, there's minimal kinetic energy. The particles might even kind of collapse in on each other. You know, they're not moving apart, so they kind of become a lumpy, I don't know, something. We've not seen this, but this is the fifth state of matter that is theoretical, and it's called a Bose-Einstein condensate, because the two scientists that kind of proposed this idea. Anyway, that's a side thing. The temperature is called absolute zero, or 0K for Kelvin, capital K, because you can't get colder than this temperature, okay? There's no, matter can't be colder than that. It can't take up space beyond that, so therefore you can't have a temperature below that. You can't have negative volume. It just doesn't work. So, because matter takes up takes up space, so has volume and has mass. So without volume, is it matter anymore? It gets all really crazy theoretical there. We've never gotten to absolute zero, though we can get quite close in small, areas in science labs, not for real. So Lord Kelvin was the person who actually proposed it, and that's why it's named after him. So basically, for the Kelvin scale, which we're going to use in this, We start at 0K, which is minus 273 degrees Celsius. And every 1 degree going up, so 1 degree Kelvin, will be minus 272. Okay, and 2 Kelvin, minus 271, etc. Going all the way up. So 1 temperature increase, 1 temperature Kelvin. Really good for us. So don't worry about Fahrenheit. We don't have to do that. Just 1 degree, 1 degree. So at 0 degrees Celsius, the Kelvin scale is 273 Kelvin. And at 25 degrees, the Kelvin scale is at 298 Kelvin. And that is 25 plus 273. So if we're converting Celsius to Kelvin, we get our temperature in Kelvin, and we get our temperature in Celsius plus 273 is our temperature in Kelvin. If we want Kelvin to Celsius, we get our temperature in Kelvin, take away 273, and we get our temperature in degrees Celsius. Now, to remember this magic number here that we're using here and here, you can actually look on your data sheet where it tells you the mole of ideal gas at 100 kilopascals and the two different temperatures here. They give the temperature to you in 0 degrees and at 25 degrees. They're a bit more precise because it's 273.15. Fantastic. Still rounds up to 273. But you can actually see it reminds you that number, 0 degrees, 273. Okay, so you know that's the number you need to add or subtract to change between Kelvin or between Kelvin and Celsius. Let's do a bit of an activity with this now. Okay, so we have a hot air balloon. It's at 273 Kelvin and it has a volume of 355 litres. So if we increase the temperature in this balloon to 395 Kelvin, keeping the same pressure, what's the new volume of the balloon? So this is where one thing we're using, there's our law, and this is where we do V1 over T1 equals K equals V2 over T2. So we remember this relationship because we have V1, 355 litres, T1, 273 Kelvin, V2, don't know, that's what we're trying to find, and T2, 395K. It's really good when you're doing these practices and stuff to actually write these things down. So 355, that was V1, and that is T1, okay, and T2, V2. So to get V2 on its own, there's V2 here, it's divided by T2. Multiply this side by T2, multiply this side of the equation by T2, and you get the formula V2 is V1 times T2 over T1. Okay, if algebras have a difficult thing for you, that's something to talk to me about, and we'll look at a few activities to practice and get the idea of what's going on there. All right, substituting in V1 355 times T2 395. Divide that, do that first, then divide by 273. Our volume is 514 litres. All right, so that is our second major law that we're going to look at here. Do some of the questions, and we're going to have a look at Gay-Lussac.